Now here we have simulated a simple power system comprising of source supplying load power to a load through this transformer, and one extra switch can be assumed as circuit breaker is used, which is initially at on state. So it's a controlled switch that can be controlled. Its operation means it's switching on or off is controlled by a control signal given to this control port. Now you can see the load current, which is the current at the secondary of this transformer. If we take in this example, in this problem, we have taken a 400 by 200 volt transformer. So as it is 400, it is 200. The current here will be just half in this circuit. Okay, so if it is 20, then it will be 10. So to make both the current same, what is actually done, we can directly take this current, but here the double current should be made half. That's why it is 0.5 is multiplied with that current, so that this current and this current are same. Understood? As here the current is double of this, so this current should be made half to get the same current. So this is the current I2 and this is the current I1. We have to find out the difference of these two current. Then we have to find out the through current, that is the average of these two current. And for that we use these blocks. So to get the difference, so this is plus minus I1 minus I2. Okay, and to get the I1 plus I2 by 2, this is done. This is the I1, it is sent to the summing block. This I2, that is also sent to the summing block, and it is divided by or multiplied by 0.5, means divided by 2. So this is the through current and this is the differential current. Okay, so logically we have got these two, and we have to take this type of block, which is known as the user defined function, where we divide this signal, we divide this with this signal, U1 divided by U2. So U1 is the differential current and U2 is the through current or average current, and this point is the bias setting. It may be 0.2, it may be 0.3, it may be 0.4, and any of these three. So suppose if we set at 0.3, and we have to see whether these bias, if the fault occurs, or there may not be fault, but it always check this ratio, and if it is seen that it is greater than the said bias, then it gives output, and if it gives output, means the NOT gate will be, the output of this NOT gate will be 0, and this 0 will operate the circuit breaker, means the circuit breaker will be in open condition. When 0 comes here, the circuit breaker will be off, so no current will be flowing if it is satisfied. Okay, and one thing it did, To simulate the internal fault, we used this block, this fault block, single phase fault. And there may be 3 phase, but any one of the phase should be activated. Other 2 should not be activated. Okay, so in this way, a single phase fault block can be designed, and the fault resistance can be varied. As I've said, the fault resistance can be varied from any low value to high value, so that we can take the readings of these for different fault currents. And the fault current can also be seen by this scope with the help of this current measurement block. And this fault also is not a, it is operated or it is controlled by an external pulse or external signal. So I can initiate the fault at any time as per my choice. Okay, so so in this way, for any fault resistance, we have to run this circuit and we have to check at which point at the operating time, if it is satisfied, then obviously this circuit breaker will open. And we have to note when it is activated and when the circuit breaker is being opened. So that is the operating time. So here the procedure means the parameters of every components are given, and where are they, where you can get this in library, also been specified here properly. So RMS block is there. One thing is very important, RMS value. So here actually I have introduced 2 RMS block, that is continuous RMS, I1 minus I2. So before that it is not a RMS, it's a signal. So the signal cannot be divided by another signal. What we are doing, that signal, we have to take the RMS value of this differential signal. And here we have to take the RMS value of this average signal. Okay, so we are getting some value. Then we have to divide this by this. Okay, and if it is seen that it is greater than this set value, then it will be 1, this will be 0, and it will make the circuit breaker open. So no current will be flowing. But in the normal case, it will be seen that it is less than 0.3. So it will be 0, this is 1. So this will be always in closed condition. The normal current will be flowing through this transformer. So in this way, the transformer can be protected from any internal fault. Okay. And this fault point is very important. The fault has been occurred between this current element and this current element. If you take this fault current, after that, then there will be no such effect. The relay will not operate if the fault occurs here, or if you connect this fault point here. Okay. So all the parameters are given here, where they may be obtained in the library. It's been given. Then in the first case, when the relay is not connected, no fault is there, then we have to get the steady values of the input and output currents, and the source current. Its RMS value as well as the phase angle, and that is obtained from the power grid block, the steady value. Now, then in the second procedure, But we have to do this fault block should be connected, as well as the relay should be simulated as the above manner. Then you see the fault path starting. You have to put different fault resistances in the fault path. So first of all, wire shifting, it is set at 20, and the fault point resistance is increased from 40 to 200 instead of 20 ohm. Get the fault current, the maximum RMS, CRMS of the differential current that is obtained from the CRO block, which is connected with the output of the continuous RMS block. Similarly, the maximum RMS, continuous RMS, is obtained from the CRO connected at the output of the continuous RMS of the through current. Then I1 minus I2 divided by I1 plus I2 by 2. This 2 will be just below this line. Then time when the circuit breaker opens, that can also be obtained from this CRO this year. That can also be obtained from this CRO or this CRO. So there will be a sharp change of the current, and you have to write the remark, either it is trip or block. If the relay operates, then trip, and if it doesn't operate, means if this ratio becomes less than the bias setting, then it will block. So we have to take the readings of for the different fault resistances. For 20% it is 40 to 200, for 30% setting 40 to 140, for 40% setting it is from 40 ohm to 120. Okay, and the report you have to submit the operating time versus percentage bias curve for different bias setting. Okay, so try to understand all these things yourself and try to do it yourself in MATLAB simulating and submitting time. Thank you.